Right, let's go to question 4. This one says that the magnitude of the gravitational potential on the surface of a planet of radius r is phi. The planet can be considered to be an isolated sphere. On figure 2.1, sketch the variation of the potential with distance x from the center of the planet for values of x between r and 4r. Right, so the first thing that we have to understand here is that gravitational potential, the graph will always be in the negative side because, as we said above, it's an attractive force, right? And at infinity is when it's 0. So when the radius reaches infinity over here, that's when it will reach 0. But below it, all of this will be in the negative side. Now, regarding the plots for it, we have an initial value, which is for radius r, we have phi. So for radius r, we have phi, but don't keep positive side. We have to keep it in the negative side. So this will be our first plot here. Now, to get other plots, we can just use the formula, which says that phi is negative gm over r. So what happens when I go from r to 2r? So what happens when I increase this by 2? What will be the value for this one? Because these two are constants, this one will decrease by 2, right? So I'm just increasing this by 2, which means this will decrease by 2. So if this was phi, now it's going to be negative, and it will be half phi. So it's going to be over here. Then what happens when I increase this by 3? When I increase this by 3, this one will decrease by 3. So if it was phi, it's going to be 0.33335, right? So it's going to be somewhere around, this is a very rough sketch, but somewhere around here, I'm not sure. For when you increase this by 4, this will decrease by 4. So this is going to be around 0.25. So your graph will look something like this. Yeah. Okay, next one. A satellite is in a geostationary orbit above the Earth. Again, geostationary orbit. Quick recap. It goes from west to east. If it's in Earth, then the period is 24 hours, and it also travels in an equatorial plane. At time t equals to 0, the magnitude of the gravitational potential due to the Earth at the location of the satellite is phi. So again, they've given you one plot that at time t equals to 0, it's going to be phi. So again, we just skip the plot directly. On figure 2.2, sketch the variation of the gravitational potential due to the Earth at the location of the satellite for values of t between 0 and 24 hours. So between 0 and 24 hours, how much will the gravitational potential change? And one thing to observe here is that the x-axis is the time in hours. It's not the radius, right? Above here, in this graph, there was radius. And this time, it's just normal time, okay? So again, we use the formula phi equals to negative gm over r. I don't see time anywhere in the formula over here. So that means that the gravitational potential will be the same throughout the whole 24 hours because the radius is not changing. This radius is constant. The mass is constant and the gravitational constant is constant, obviously. So this is going to be a straight line. I tried my best. And that's it for question 4. We have now reached the last question of this paper, and this one is from May-June 2019. It states that there is 2 point masses which are isolated in space and are separated by a distance x. State an expression relating the gravitational force F between the two masses to the magnitudes m and m of the masses, and state the name of any other symbol used. So again, we know that gravitational force is equal to g mm over, now just be careful here to not write r because they say they're separated by distance x, right? So we'll write x squared. And state the name of any other symbol used, which is this g, and g is the gravitational constants. So that's it for this question. The next one says that a spacecraft is to be put into a circular orbit around a spherical planet. Again, circular orbit. The planets may be considered to be isolated in space. The mass of the planet, assumed to be concentrated at its center, is 7.5 times 10 power 23, and you are also given the radius of this planet. The spacecraft is to orbit the planet at a height of 2.4 times 10 power 5 meters above the surface of the planet. At this altitude, there is no atmosphere. So again, let's visualize this. You have a planet over here, and you have a spacecraft. You have your radius of the planet, which is 3.4 times 10 power 6. So this is the radius of the planet, and they say there's an additional height h of 2.4 times 10 power 5. And you have to find the speed of this aircraft, and you have to show that it's equal to this one. Again, because they said it's a circular orbit, we'll use ft equals to fc, and we will write gmm over, I'll just prefer to use x here because that's what they said in the question, equals to, now fc we have two options. We use mr omega square or we use mv square over r. In the question over here, I don't see any sign of period time, and I don't see any sign of angles or rotations. But here we have to find the speed, and you know that in mv square over r, the v represents the speed. So this will be more appropriate to be used in this question over here, right? And this is obviously x. So now we can just plug in the values, and g will be 6.671 times 10 power negative 11. We have the mass to be 7.5 times 10 power 23, and this m cancels out, so we don't need that. And this is equal to, so let me just do this, and between x square and x, you can see that this x over here will cancel out with one of the x here because it's x square and this is x, so this will just be x, right? And x was now x is the separation, so it's going to be the radius of the planet plus this height over here. So this is going to be 3.4 times 10 power 6 plus this height, which is 2.4 times 10 power 5, and all of this is equal to v square. And when you do the math, you will see that v is equal to 3.7 times 10 power 3. Okay. Next, it says that one possible path of the spacecraft as it approaches the planet is shown in this figure. The spacecraft enters the orbit at point A with speed 3.7 times 10 power 3. So it's going from B to point A, and it's still in this orbit around the planet. At point B, a distance of 5 times 10 power 7 meters from the center of the planet, the spacecraft has a speed of this much, and the mass is this much. For the spacecraft moving from point B to point A, show that the change in GPE of the spacecraft is 8.3 times 10 power 9. So we have to find the change in gravitational potential energy. For that, what is the formula for GPE first of all? GPE, we know that is equal to negative G mm over R. Right, now we want to find the change, so we always do final minus initial. So you will have to do GPE at A minus GPE at B. So what we can do here is that the change in GPE equals to GPE at A minus GPE at B. Okay, and GPE at A will be equal to, let me just write this nicely, GPE at A equals to negative G times, the mass will be 7.5 times 10 power 23 because that's what's given here, 7.5 times 10 power 23 times the smaller mass will be 650 divided by the radius, which is 5 times 10 power 7. So this will be the GPE at A. And for B, you will have the exact same thing, and it's just that the radius over here will be 3.64 times 10 power 6. So this will be G times 7.5 times 10 power 23 times 650 again. Now, when you do this subtraction over here, note that there's also another negative over here because that's part of the formula, right? So GPE at A is this part, GPE at A is this part, and GPE at B is this part. And we are finding the difference between GPE at A minus GPE at B. Yeah, and when you do the calculations, you should get the answer as negative 8.3 times 10 power 9. You can just ignore this negative because the negative just indicates that it's attractive, right? So it's just saying that the GPE has been decreased from B to A. So this was more further out, but this is more near, so the GPE will decrease, right? And that should be your answer. Last question is that by considering changes in GPE and in kinetic energy of the spacecraft, determine whether the total energy of the spacecraft increases or decreases in moving from point B to point A. So let's look over here. The first thing is that we know that the GPE has decreased. Why? Because it's negative over here. And you can also show this by the graph of GPE. Remember the graph of GPE against radius. The graph looked something like this. So the radius, if it is more, the GPE is more. But if the radius is less, the GPE is less. You can see that the radius here has decreased. You went from something times 10 power 7 to something times 10 power 6. So we are decreasing GPE. So the GPE is getting lower, right? So the first thing that you can say is that the GPE is lower. And how about the kinetic energy? To know about the kinetic energy, you can just look at the data over here. Kinetic energy we know is half mv square, right? That's kinetic energy. You can see that at point A, the speed was 3.7 times 10 power 3. But at point B, the speed was 4.1 times 10 power 3. So if you go from point B to point A, you are decreasing the kinetic energy. So even the kinetic energy was getting less. And because total energy equals to Ke plus GPE, and both of these are decreasing, so obviously the total energy will also decrease. Right, that's it for this topic, and I hope you got a good understanding of gravitation and how to answer these questions. Thank you for watching.